In this video, we'll investigate when is a function differentiable. In previous videos, we've discussed how to determine a function's continuity, and I think that continuity will help you to understand the concept of differentiability. So I strongly recommend checking out previous videos, and you can find all the links down below. And in today's video, we'll explore conditions that make a function differentiable. To summarize, when determining the continuity of a function, we take a certain value and we look at the limit of the original function as x approaches this chosen value from the positive and negative directions. And when it comes to differentiability, we use a similar method, but instead of looking at the original function, we look at the derivative function. In other words, the limit of the derivative function. For example, the modulus function or the absolute value function is given by, so f of x is equal to the absolute value of x. If we differentiate this function, we have 1 and negative 1 respectively, because the derivative of x is 1 and the derivative of negative x is negative 1. This means that the gradient to the left of 0 is negative 1. And the gradient to the right of 0 is positive 1. So we can see from the domain. The two values are not equal, so we conclude that the modulus function is not differentiable. Alright, in this example for this function, we can figure out the derivative functions. The derivative of x is 1, and the derivative of negative x is simply negative 1. Sketching these two functions, y equal to 1 and y equals negative 1, we have the following graph. So basically two horizontal straight lines at y equals 1 and y equals negative 1. It's clear that the derivative does not exist at 0 since the derivative function is not defined. So that's our conclusion. Now, we know that the derivative of a linear function is a constant, and it's equal to the gradient of the linear function. In other words, after deriving a linear function that's usually in the form of y is equal to mx plus c, now since it's linear, the constant term c disappears and the derivative function becomes a constant, which is the gradient m. And in this graph, we can figure out the derivative, the gradient of the linear function, by looking at its rise over run. The gradient as x approaches 0 from the left side is, so rise is 2 units and run is 1 unit. So that's 2 over 1, which is 2. So we know the gradient equals 2, right? And the line is going up, so the gradient is positive. The gradient as x approaches 0 from the right-hand side, the rise is 2 and run is negative 1 because the line is going down. So we say that the gradient equals negative 2. So if we sketch these two functions, y equals negative 2 and y equals positive 2, we have the following derivative function graphs. And it's clear that the derivative does not exist at x equals 0. So that's our conclusion. So our conclusion is that the function is not differentiable at x equals 0. Before we continue, it's shown in the previous section that some piecewise defined functions are continuous everywhere. So we've shown this. And similarly, the piecewise defined functions which are differentiable everywhere. To determine the differentiability of these piecewise defined functions, we look at the smoothness of the joins. In this example, let's take 2 steps. Step number 1, let's find the derivative functions. For this piecewise defined function, we can easily find the derivative function by differentiating it. So the first function, if we find the derivative, it becomes 2x plus 2, and the constant term 1 disappears. So that's what we have here according to the same domain. For the second function, by differentiating, the constant term 1 disappears and we're left with 2 only. So that's how we obtain the second function, the second derivative function. Second step is to sketch the derivative function according to the domain. It's clear that when x equals 0, the derivative function evaluates to 2. And if we go back and look at the original function, they also join smoothly at point 0, 1 because that's the common y-intercept. So we can say that the derivative function when x approaches 0 is defined and it's equal to 2. The two sections of the graph of the original function also join smoothly at the point 0, 1 because that's the common y-intercept. In the last example, let's still follow the two steps. Step number 1, find the derivative function of the piecewise defined function. Again, let's differentiate, okay? So the first one becomes 2x plus 2, the constant term 1 disappears. The second function becomes 1 and the constant term 1 disappears. Once we obtain the derivative function, let's now take the second step and sketch the derivative function according to the domain. It's clear that when x approaches 0 from the left and right of the function, the derivative function evaluates to 2 and 1, right? Because if we approach 0 from the right-hand side, the value approaches to 2, whereas if we approach from the left-hand side, the value approaches 1. Since the two values are not equal, we conclude that the derivative function as x approaches 0 is not defined, as the limit from the left and right are not equal. Therefore, the function is differentiable for any real values except 0. Okay, I hope you find this video helpful, and I will see you in the next video. Bye!